and hopefully the connection will not drop. Okay. You can all see the slides?
Yes.
Yes, excellent. That was a very heavy yes. İrfan Bey. Pelin Gezer. We used to have a student, Pelin Gezer, a few years ago. This is a different Pelin Gezer, right?
No, same.
No, the same?
Yes, I just started working
Yes.
3 years ago. Now I realize I have still a chance to finish. So I'll give a chance because I'm thinking to move abroad. Actually, this summer.
Well,
Career is going well.
Yes.
I'm at IBM as solution architect in the AI group. So let's see.
Well, good luck to you. I hope everything works out. Okay.
This is good and sad at the same time.
This is a what?
This is good and sad at the same time.
Good and sad.
I mean, if you work hard enough, they don't ask you about the graduation. Well, it was a hard way for me, but I did it.
Well, it helps. It doesn't hurt to graduate. That's for certain. Well, good luck to all of you in your professional careers. Hopefully, I mean, this is the beginning of the end. But also keep this in mind, from my own personal experience, regardless of which engineering field you have chosen, computer, electronics, mechanics, industrial, etc., the third year of your education is the toughest one. So I'm sure that you have experienced this during the first semester, but the second semester with system programming and operating systems and everything, this will be a tough year. It is a tough year, and plus we have the pandemic on top of it. So yeah, so good luck to everyone. Okay, introduction, what is this course about? Let's see. You have your slides available on Moodle, so you can check them from there too. So this first lecture will be basically an overview of everything. An overview of everything, a review of the entire semester. So we will talk about everything included in the curriculum, but very, very superficially, just to get a feel, just to get an idea of what we will be dealing with in the context of this course. Now, the aim of this course is to make the students familiar with system-related calls of a POSIX-compliant operating system. So we will be dealing with system calls. We will be dealing with something called system calls, but not just any system calls, but only the system calls related to a POSIX-compliant operating system. Now, there are many questions now. What exactly is a system call? What does it do? What is a POSIX-compliant operating systems? Why do we need POSIX-compliant operating systems? Why do we have to use system calls, etc.? Now, the system calls are basically just function calls. System calls are very simply functions available to us, the developers, in order to interact with the operating system. Why do we want to interact with the operating system? Because basically, unless we interact with the operating system, the programs that we can implement are very, very limited in terms of function. You can only write programs that can calculate something. You can put a few values to a you can give a few values to a few variables, multiply them, add them, calculate something, and that's it. Even for the simplest of things. What's the simplest thing that you can do with a result? Print it on screen. Even for printing on screen, you have to interact with the monitor. And for interacting with any piece of hardware on a system, you need to go through the operating system. Why? Because as you are seeing, and as you will see in the context of the operating system course, the operating system is the god, if you will, of the system. It's the boss, the only boss in the system, and everything goes through it. The processes, and by process I mean the working programs, are extremely limited when it comes to what they can do in that system. They are very, very limited, and for anything that has to do with interacting with the actual system, they have to go through the operating system. And the only way to go through the operating system to make a demand for a certain service, for printing on screen, for writing to a file, for synchronizing with other processes, for creating a thread, etc., they all go through system calls, those very special functions that are provided by the system. So if you can deal with system programming, if you can program towards the system, if you can manipulate the system calls, you can talk to the operating system, tell it what you need. You can access hardware, all the hardware available, and that is accessible to you. So just because you can call a system call, it doesn't mean that you can access everything. You also need the permission of the operating system for that. And of course, you can perform low-level programming. Now, a very often question by students is, yeah, hocam, yeah, I'm not going to develop mainboards. I'm not going to do low-level programming. Why do I need system programming? Why is this course mandatory? I'm going to work on distributed systems. I'm going to work with Java, C#. I'm going to do full stack programming or backend programming or whatever. I'm going to write in the I'm going to write in the Python. I'm going to become a data scientist, etc., etc. So why do I need system programming? Why is this mandatory? That's a good question. Because if you're going to work with, I don't know, with Python on machine learning, or I don't know, become a computer vision specialist, etc., do you really need to know about signal handling? I mean, do you really need to know about inter-process communication? Really? Semaphores? I mean, is that really necessary? No, very not necessary. I mean, I wouldn't say necessary because you're not going to really use signals for communicating in your everyday life. Very probably you will never use them if you go in that direction. So why is this course mandatory? Sorry. I'm sorry for that. So why is this mandatory? Now, because the concepts that are explained here, the concepts that are explained in the context of this course, they are valid not only in the course of C, not only in the context of C, but they will also be of use. Not all of them, but a certain part of them will be of use to you. One, no matter what the language you use. And also, the intricacies, the details that we're going to see will enable you to understand in a sufficient level of detail how exactly things work behind the curtains. And that will enable you to master those skills. Because right now, let's say that you're working with Java. Let's say that you have graduated and you're working with SQL queries. You're writing SQL queries for Oracle using Java. I don't know, PLSQL, etc. Or I don't know, you're a backend developer for somewhere using C# or etc. Who knows? Whatever. You will be using threads. If you're working with Java, you will use threads. If you're working with C#, if you're working with a serious programming environment, you will need threads. And this is the only course that is available for you where we will see exactly how those threads work, and more importantly, how to synchronize threads. Because that is one of the main issues that you deal with in a multi-threaded environment. Now, I know that very probably you have already seen threads in different contexts, but never in detail. Now, here we're going to take a serious look on what is happening behind the scenes with threads. Personally, I mean, not as a professor of this course, but just as a person who has graduated from computer engineering almost 20 years ago, the value of this course is in terms of only two things. Now, if you are taking a path that is leading you to low-level programming, all of this stuff will be very valuable to you. So if you're going to work very closely to hardware, this stuff has a value of gold to you. However, even if you do not take that path, even if you work in something unrelated to low-level programming, the two fundamental things that will benefit you from this topic is, one, how to synchronize multiple processes and threads, because you will need that no matter what the language you work on. And second, how to communicate, how to exchange data between processes and threads. Those are the two things that are necessary for you, no matter what the language you work in the future. But if you also take a direction towards low-level programming, of course, all of this stuff will be very highly, will be invaluable to you. Mr. Kamil says, why do we separate user mode and kernel mode even though it is expensive to switch between them? Why don't we integrate these so the system calls would be faster and efficient? We didn't get that to yet, Mr. Kamil, yet. Step by step. So in this course, we will take a look at the standard C library. I mean, you know about the standard C library. It's not really the standard C library that we care about. It's more about the POSIX system and the system calls. Look at the standard C library, how we can use it, the standards of OS level programming, because yes, there are standards, there have to be standards. And of course, how the theory of operating systems is applied to the practice of actual systems programming. I mean, you will see many nice ideas, many nice principles, nice theories when you work with Yusuf Sinan Hoca in the context of operating systems, but somebody needs to implement that stuff. And when it comes to practice, I mean, you can design systems with multiple processes synchronizing with each other, but designing them is one thing, and actually implementing them in a portable way is a completely different thing. So, programming interfaces. What about programming interfaces? Why do we care about programming interfaces? Programming interfaces allow applications to perform tasks. What kind of tasks? File input output, creating, deleting files, creating new processes, communicating between processes and threads on the same computer or on different computers, etc., etc. The set of low-level interfaces is known as the system programming interface. Now, what's the deal here? Now, the deal is the following. Imagine this scenario. Imagine that you have written a program. This program interacts with the system. Maybe it creates files, maybe it deletes files, maybe it creates multiple processes, whatever. You have coded it, you have used C or whatever language, it works on your system, it works with your CPU, it works with your operating system, everything is perfect. Now, the main issue with programs that work at a low level is portability. Portability, taşınabilirlik. This was the main problem that they had in the 60s, 1960s, in the 1970s, in the 1980s even. There were multiple processor architectures, multiple operating systems around, and the problem was that every program that was created was not portable enough. Imagine a program where you have the printfs, you have functions for creating files, closing files, etc., for creating shared memory units, shared memory segments, a lot of things that have to interact with the system. And as soon as you take it to another computer with a different CPU and a different operating system, you have to rewrite all of those parts so that it will work on that different architecture, on that different operating system. That is a huge waste of time. So even as early as the 1960s, when people were designing the first kernels, the first operating systems, such as Multics and Unix and so on, they thought about this problem and how to make it portable. And the simplest idea that they could come up with was, let's make a certain interface, bir sözleşme, a contract, about how to do certain things. Do you want to open a file? These things will be the parameters. This will be their meaning. This is what the system will do, and this will be the output. And no matter what the operating system is, no matter how your architecture works, you have to comply with uymak. You have to comply with that contract, that set of rules or programming interface. That's why we have those system programming interfaces, so that the programs that we develop will be portable, so that when you write printf, etc., do something, or open the file at that path, etc., you know that system call, what it is going to do. You know which parameters that it admits. You know in which order it expects those parameters. You know what it is going to return if there is an error. You know what it is going to return if it succeeds, etc., etc. And you can take the same file, compile it on a different computer with a different operating system, and still expect that system call, that file opening part, to work as expected, as designed. That's why the standards are important. That's why system programming interfaces are expected to be implemented by all the operating systems. Now, what exactly do we mean by operating system? The term operating system is commonly used with two different meanings. One, of course, to denote the entire package consisting of the central software managing a computer's resources, and all of the accompanying standard software tools such as command line interpreters, graphical user interfaces, file utilities, editors, and so on and so on. So the entire bundle, the part of it that actually manipulates the hardware, that manages the hardware, plus all the accessories, command line interpreters, the shell, the graphical user interfaces, and so on and so on. That's the entire package. But more narrowly, of course, the operating system can also refer to the kernel. So basically, that is the fundamental part of the operating system, the core, çekirdek, the core of the operating system that carries out the responsibilities that are absolutely necessary for the computer to function. And that is, of course, managing and allocating computer resources. And what are the computer resources in a system? Well, basically, the CPU and memory, and of course, access to devices. The operating system is nothing but a set of functions, really. It's just a set of functions. It has a huge responsibility. A huge responsibility. That is why it is not in vain that people say that the two most complicated pieces of software today in 2021, the two most complicated pieces of software are operating systems. And what is the other one? Any guesses?
Compilers?
No, games. Games. You know, the big ones. They are really, really large projects, operating systems with tens of millions of lines of code. I mean, that's how you measure the size of a project. Well, one of the ways of measuring the size of a project in terms of lines of code, tens of millions of lines of code. Operating systems, games, autonomous vehicles. They have tens of millions of lines of code. So why are operating systems that complicated? I mean, they just have to manage manage the devices, allocate computer resources. I mean, why should that be that complicated? Because the kernel has many responsibilities. It performs process scheduling. What is process scheduling? Basically, it has to decide which program is going to run when and for how long. You only have one CPU, very probably. And that CPU must be shared by everyone. The kernel needs to use that CPU. The programs want to use that CPU. Everybody wants to use that CPU, but nobody can use it constantly. So it is the kernel that needs to decide how long each process will allocate CPU time. And when that time is up, it is the kernel that will take it away from the CPU and signal another process telling it, now it's your turn. Now you can execute. And of course, you have to do it in such a way that you must be fair and just towards all the processes. Well, give or take a few parameters, such as priority. That's a very important responsibility. And there are many different algorithms for scheduling those processes. You will see about them in your operating systems course. Memory management. The kernel needs to manage the memory. The kernel, I mean, you have a finite amount of memory. Maybe you have, I don't know, 8 gigabytes of RAM, or maybe you are rich and you have 32 gigabytes of RAM, who knows? And all of the processes, including the kernel, by process I mean a running program, they want to use that memory. They want to use as much as they can from that memory. So you have, as a kernel, you have two responsibilities. One, you need to respond to those programs when they want to allocate memory. So let's say a program calls malloc or calloc, and they want 1 GB of memory. Well, you have a total of 8. So somehow you need to figure out which part of memory you are going to allocate for that process. Or maybe you can't. But let's say that you did. Let's say that you succeeded in allocating that piece of memory. You have another problem. What happens if some other program tries to access the memory of another program? Let's say that you are running a banking application, and at the same time, there is a malware, a program with bad intent, with malicious intent on your program, a Trojan, a rootkit, something. So if the operating system doesn't protect the memory of those processes, that malware might be able to just, go to that part of memory and check the variables in your banking application. So it is the responsibility of the kernel to protect the memory regions of each process from the potential access of other processes. And what happens if you access a memory region that doesn't belong to you in a process? So let's say that you write a program in C and you randomly say access memory location 0x123456789110. What happens then? Have you tried it? Ever?
Segmentation fault.
Yes, a segmentation fault. That's the way of the operating system telling you you are not supposed to be accessing that part of the memory. Exactly. The operating system is providing you with a file system, an organization of all the files on your hard drive so that you can easily access them by name. That's a really large data structure there. And it needs to be efficient enough to manipulate files very easily. Copy them, paste them, move them. Creation and termination of processes. Let's say that you have a running program and you want to start a new program. How do you tell the operating system to start a new program? How do you start a new process? Through the operating system. So it needs to also provide that service. It needs to obviously provide access to devices. You want to access the scanner, the monitor, the printer, the graphics card, the GPU, I don't know, the hard drive, anything. You go through the operating system. Networking. You want to send even a single byte to another computer. You want to read your email. You want to do anything. You have to go through the operating system. You cannot just go directly to the network card and just tell it, hey guys, can you send this package to this computer in Malaysia? No, it doesn't work that way. Your process, what it does is, through the system calls, it very kindly asks the operating system, please, can you access this device in my name and carry out this operation and let me know how it goes? That's how it works. We, or the processes that we develop, they use the system calls to kindly ask, they are not ordering, they are kindly asking the operating system to carry out an operation, a low-level operation, in our name. And the operating system might do it immediately, it might postpone it. He is the boss. So whenever the operating system thinks that it is convenient for him, then it will carry out your operation. And what about the process? What does it do in the meantime? It waits. You call a system call, you carry out a system call, and then all you can do is wait. For what? For the operating system to complete that operation and get back to you. A computer, of course, is one or more central processing units, often only one, which execute the instructions of programs. And in Unix systems, we use preemptive multitasking. They are preemptive multitasking operating systems. What does it mean, preemptive? What does it mean to be preemptive multitasking? Multitasking means that you can have multiple processes running programs at the same time, sharing the same memory, each using a time slot on your CPU. as opposed to being single tasking. Can you give me an example of an operating system that is not multitasking? I don't know if you have encountered real-time operating systems. Yes, well, certain versions, yes. In my time, for instance, the most popular one was DOS, MS-DOS. Yes. It was a single task operating system. So you just enter a command and you wait for it to finish. You cannot do anything else in the meantime. Preemptive means that the rules governing which processes receive use of the CPU and for how long are determined by the kernel process scheduler and not by the processes themselves. So the processes cannot just say, hey, I'm going to take the CPU and I'm going to work with it for the following 5 minutes. Why? Because if you allow that, that means any process can just allocate time for as long as it wants, and no other process can work in the same time. Let's say that you want to execute, I don't know, Firefox and connect to the web, but no, you can't. Why? Because LibreOffice is working right now, and it has decided to work for 10 minutes. So you have to wait for LibreOffice to finish. And then you will be able to switch. So preemptive multitasking, multiple processes at the same time. Preemptive, it's the kernel that decides when to switch whom, for how long, and when to stop them. So basically, processes have no rights whatsoever. So, I mean, let's put this clearly. The computer is a dictatorship. There is only one person that is valid, and that is the kernel itself. The kernel decides everything, everything. And the processes have no rights whatsoever. So, and there is nothing we can do about it. That's how the operating system is designed. You need to accept that. Kernel tasks and memory management. Now let's take a closer look. Typo here. Let's fix it. Physical memory is a limited resource that the kernel must share among processes in an equitable and efficient fashion. Most modern operating system employs virtual memory management, a technique that confers two main advantages: isolation from one another, and only part of a process needs to be kept in memory. Now, we will of course have a separate week for each of these concepts, so don't worry about it. This is just a superficial overview of what is going on. The main idea that you need to know about memory, the main principle that you must never forget when it comes to memory management is the following. Every program, now for instance, right now, I have a large number of programs going on. I have process IDs up to the 15,000, 16,000. So I have hundreds of programs running right now, and every single one of those programs, except for the kernel, of course, thinks that it has full access to the entire memory. Of course, that is not true. I mean, we have thousands of processes working at the same time. So each of them is only using a part of the memory, but each of them is also under the illusion. Each of those processes is under the illusion that the entire memory is available to it. That's what virtual memory succeeds in. Each process thinks that the entire memory is his, and he can allocate as much as it wants, whenever it wants. That's what's virtual, because it is not true. Not true. Why? Why do we do that? For two reasons. Thanks to virtual memory, the kernel succeeds in isolating one process's memory region from another one. So thanks to virtual memory, thanks to this mechanism of virtual memory, the kernel can keep track of who is using what. And if you try to access the memory region of some other process, the kernel can very easily send a segmentation fault to you and stop you from doing that. No matter who you are, no matter what kind of permissions you have, you cannot access the memory region of another process. Absolutely forbidden. And the second advantage is, of course, you do not have to keep the entire program in memory, thanks to virtual memory, thanks to this mechanism. It allows you this. You do not have to keep the entire program in memory continuously. Only a part of it, if necessary, and allocate accordingly. Now, we will have a separate week for all of these concepts during our semester. Provision of a file system, of course, the kernel provides with a file system on disk, allowing files to be created, retrieved, updated, deleted, creation, termination of processes, etc. Now, we will be using the term process very often, so let's get this clear. A process is a running program. If it is not running, it is just a program that is on your hard drive. But if it is actually running, so you have executed it, double-clicked it, or whatever, now it is a process. Here, for instance, each line of these is a process. You can get them by using the PS command. Each of these is a process. And of course, the kernel is responsible for all of them. The kernel creates processes. The kernel terminates processes. The kernel allocates resources for processes. The kernel frees the resources for the processes. The kernel keeps track of everything concerning processes. Everything. Accessing, of course, devices, also among the kernel tasks. And of course, not only access to devices, not only it allows us as developers to access devices through our programs, but it also gives us an interface that standardizes and simplifies this access, while at the same time allowing multiple processes to access each device. Let's say that you have two processes that want to access, the hard drive at the same time. Let's say that you have two processes that want to access, the DVD player or the GPU at the same time. How do they share it? Who gets to use it first and for how long? Do they get to just finish whatever they have to do and then the other one works? Or do they complete a part of it and then the other process completes a part of its task and then they switch? How does it work? That is all up to the kernel. We will get to that in a separate week during our semester. And of course, networking. Networking will allow you to actually exchange data, between processes that are in different computers. So communicating on the same computer is already difficult. Why? Because it is forbidden to access somebody else's memory. So how do you communicate with them? Do you write to the hard drive and expect the other process to read from that file? Well, you can do that, but it's not really that efficient. And plus, you still have to go through the kernel. So it is already difficult to communicate even when you are on the same computer. And imagine now two processes on different computers. Firefox on my computer and the web server at the other end of this world. The web server, Apache, for instance, is also a process. Firefox here is a process. Mine is a client, that's a server, and they need to communicate. I send a request wanting a certain page. Apache responds with the contents of that page, and Firefox renders and visualizes that page. All go through the kernel, all of them. A multi-user operating system provides users with the abstraction of a virtual private computer. Now, of course, you can have multiple users. You're expected to have multiple users. And each user has its own set of processes. So it is up to the kernel to organize all of this. It's up to the kernel to simulate, to provide the illusion, if you will, to each user as if they are the only user on this computer. So maybe there are 10 users connected to my computer right now. I don't know. Well, I know there isn't anyone because I have forbidden it. That's a different thing. But if you're using a server, there could be multiple users connected to a system, all of them having created hundreds of processes, and it is up to the kernel to make sure that no user interacts with another user in a disruptive way. It has to protect the users and also allow the users to use the resources of that system. All of them need to be able to access the devices, transfer information, and it is up to the kernel to resolve all of the conflicts from accessing hardware, etc., etc. While the users and the processes are mostly unaware of these conflicts. I mean, the process only goes to the kernel and just says, hey, I'm sorry, can I use that device, please? You give your petition, dilekçeni veriyorsun, you give your petition, and that's it. Then you wait. Then the kernel checks all the petitions that it has. Maybe there are 200 processes that want to use the same device at the same time as you. The kernel puts them in an order. It decides who is going to use what. And once it has been used, it gets the result. Then it returns you the outcome of your petition. And in the meantime, your process just waits. That's why I said the processes have no rights. They can only ask for things, not order. Ask for these things from the kernel, and then wait for the result. That's the principle of how the system works. You cannot rush the kernel. You cannot order the kernel. You cannot push around the kernel. Instead, it's the kernel that orders you, which brings in mind the Soviet Russia meme. Anyway, kernel mode and user mode. Now, let's get to the question asked previously by Mr. Kamil. Modern processor architectures typically allow the CPU to operate. That's a typo. Modern processor architectures typically allow the CPU to operate in at least two different modes, user mode and kernel mode. Two different modes for a CPU. What's the difference between them? Now, the user mode also has access to certain instructions, but when the CPU is in kernel mode, the CPU is basically free to do anything. It can access any memory location. It can execute any instruction, no controls, no nothing. Full access to the entire instruction set. That's what it means to be in kernel mode. Nothing prohibited, everything allowed. Whereas in user mode, hardware instructions, whereas in user mode, certain instructions are not usable and only certain areas of memory can be accessed. There is also areas of virtual memory that are marked as user space and kernel space. The area that is marked as a kernel user space, when running in user mode, the CPU can access only memory that is marked as being in user space. So there is a certain part of the memory that is marked as kernel space that you cannot access while you are in user mode of your CPU. But if you're in kernel mode, you can access just basically anything. Now, before we go further, let's see this part, and then we can get to the question of Mr. Kamil. Now, Mr. Kamil said, why do we separate user mode and kernel mode, even though it is expensive to switch between them? Yes, that is true. It is not really that cheap to go back and forth. I mean, it's not really that expensive. I mean, you're not losing a second, for instance. I mean, just a millisecond or something. But why don't we integrate these so the system calls would be faster and efficient? Now, Mr. Kamil is asking this because he knows that in order to carry out a system call, you need to switch from user mode to kernel mode. Now, a system call is a function. It's a function that is executed by the kernel. And since this function is a system call, and it means that it is going to access devices, it is going to do some serious stuff that requires kernel mode permission, that means you need to switch from user mode to kernel mode in order to execute the system call, and then after you're done, return to user mode. And of course, that switch from user mode to kernel mode, from kernel mode to user mode, when you return, that takes time. Now, the answer to that, Mr. Kamil, is it's a question of design. Now, let's say on one hand, you do not implement this. You have no user mode, no kernel mode. What's the disadvantage? The disadvantage is that there isn't really that much to stop at the hardware level the processes from accessing prohibited memory locations and prohibited CPU instructions. It makes it very difficult in this case to establish law and order in the world of this computer. Yes, you are sacrificing a few milliseconds for those switches, but in return, you get hardware level support for protecting memory and for protecting dangerous CPU instructions. And it is worth it. People thought about it in the past. They weighed these two advantages and disadvantages, and they decided that it is worth those few milliseconds for switching between user mode and kernel mode in order to acquire hardware level support for protecting instructions, and more importantly, protecting parts of the memory from programs with malintentions. I hope it is clear at this stage. Now, another very important principle that you need to take into account when you're working with processes is the following. Never, ever forget this, especially if you're working with multiple processes and multiple threads. Now, let's forget about threads for now. There is no guarantee. There is no guarantee how long your process is going to execute before it is interrupted by the kernel and switched for a different process. In my computer right now, there are hundreds of processes working. They are all working. A few milliseconds for one, then it steps aside and another process gets into the CPU and works in its place for a few milliseconds. Then it steps away, another process comes in and executes in the CPU for a few milliseconds. Then it steps away, and so on and so on. There is no guarantee whatsoever. There is no guarantee, never a guarantee of how long your process is going to execute before being switched. It might be interrupted in the middle of a loop. It might be interrupted in the middle of a system call. It might be interrupted in the middle of anything. There is no way of telling the CPU, I want to be executed for the following 5 milliseconds, no matter what. You cannot do that. And what are the implications of this? What are the consequences of this fact? The implications are that especially when you're working with multiple processes, you need to plan ahead against this. You need to take precautions when you're working with multiple processes or multiple threads against this situation, because it can very easily ruin a context switch, a switch of processes at a time that you were not expecting it, can ruin your entire system design. So you need to always take into account and design your system, your software, as if it can happen at any moment. The context switch can happen at any moment. Never make any assumptions about how long that process is going to work for. Never. How do we take Sorry, class, I'm back. I dropped a bit, and here I am. So how do we take those precautions? Well, that will be a topic of 2 weeks during the semester. We will see about all those things, all those tools that are available for manipulating the semaphores and mutexes and so on and so on. Now, another issue, of course, is that not only does it know when it is going to time out, but also processes do not know where they are located in memory. Remember, they are all using virtual addresses. They only have a false illusion of the structure of the memory. All the processes think that they have access to the entire memory on their own. That is wrong. That is an illusion. But that's the picture that the kernel shows to them. Whereas in reality, all the processes are sharing the memory among each other and, of course, with the kernel. So the process versus kernel view, the process looks at the system and it sees it's all alone. There is a CPU to use and it has access to the entire memory if it wants to. And the kernel view is that there are hundreds of processing executing, the kernel is executing, everybody's on the same memory, and it is the complete responsibility of the kernel to organize everything. And Mr. Yusuf says, what would be the advantage if processes knew where they are located? Well, it would be easier for them, maybe, to make decisions about more efficient accessing. No, not efficient accessing. I mean, would there be an advantage for a process to know where exactly it is located? Let's say that you know that you're in the middle of the memory. Does that serve a purpose? Well, it could serve the purpose of absolute addressing. So you could directly go and access, try to access places that do not belong to you. I don't know. Doesn't make sense. I don't know about the advantages, Mr. Yusuf, but I know that there are many disadvantages to knowing exactly where you are. So the entire issue is there that you need to protect the other processes' memory from your access. So you must not know who is located where. So you have no idea who is where, who holds which variable where. You must not know it, and most importantly, you must not be allowed to access it, even if you do know it. Even if you do know that this and that address contains that variable, you must not be allowed to read it, and even more importantly, to write it, to write on top of it. So that's why we have virtual memory, to establish this, this protection mechanism. A process operates in isolation. It cannot directly communicate with another process. Absolutely. There is no way for a process to communicate with another process without going through the kernel. It cannot even create new processes. It cannot even communicate with input-output devices. It cannot even print on the screen. The kernel decides basically everything. That is why we have this picture of children playing in a sandbox, because that's how processes are in a system. They are only playing with the toys that the kernel has given them. And if they ever want to get outside that sandbox, well, depending on the parent, they will probably be beaten up. Or just kindly, the operating system will tell them, please stay inside. Well, it depends on what kind of a parent you have. Now, how does the kernel achieve all of this? Now, the kernel maintains data structures. It needs to maintain data structures. Now, imagine there is a process working. Now, what do you have to keep track of? You need to keep track of all the files open by this process. And not only which files it opened, but with which permissions it opened them. Only for reading, for writing. Where in the file is the offset? I mean, has the process read the first 5 lines? The first 10 lines? You need to keep the offset too. You also need to keep, of course, the memory locations allocated to this process. Which are the regions of memory that this process can access? You need to keep a list of them. You need to keep a list of all the signals that are supposed to be delivered to this process. You need to keep track of which functions will be called in this process in case a certain signal arrives. And many more such data structures need to be stored for every process independently. So if you have 10,000 processes running at the same time, that means you have tens of thousands of data structures in total associated with all of them. That's an incredible amount of logistic work for the operating system. And that's why it is so complicated as a piece of software. What about the shell? Sorry. The shell is simply just an accessory, an auxiliary program that comes with the kernel. Now, and all of them together, they form the operating system. So the kernel plus the shell plus the graphical user interface plus the other stuff, they all make up the operating system. The shell is just a command interpreter. So it is just a program that accepts commands directly from the user, not from the processes, but directly from the user, from the standard input. And they can be used for everyday tasks for creating, reading files, deleting files, manipulating files and devices, and so on. Now, the term login shell is used to denote the process that is created to run a shell when the user first logs in. And on some operating systems, the command interpreter is an integrated part of the kernel. Now, on Unix systems, the shell is a user process. Now, the first part of the sentence refers to Windows. Now, in Windows, the command interpreter, well, in some versions of Windows, the command interpreter wasn't a user process, but it was a part of the kernel. So if you did something stupid on the shell, you could crash the entire system. But with Unix systems, Linux systems, in general, you are safe in that regard. You can crash the shell. You can do stupid things with the shell as much as you want. You will not be able to crash the entire operating system. So it is just a program like any other. So if the shell crashes, it's just a program that crashed, that is terminated, and that's it. It cannot hurt the kernel. User groups. Now, you have been using the Linux systems, I'm guessing, since your first year, probably, or at least hopefully. So that means you're already aware that there are distinct user accounts for every user on a Linux system. Each of them is associated with a user ID, a numerical ID, so that the kernel can reference them. The kernel doesn't use, of course, your user names in order to manipulate those accounts. It, of course, uses the user IDs. And, of course, there are group IDs in order to have a group of accounts with similar permissions and similar levels of access to different various resources. And, of course, in that case, we have group IDs in order to identify those groups. You already know, of course, about the structure of the directories in a standard Linux system. Of course, we have the root at the top of this hierarchical directory structure, and the folders are underneath them. And what is the question, Mr. Yusuf? Type it in. Windows shell was giving kernel mode restrictions, not kernel mode restrictions. The shell was, in the past, in the very faulty and buggy versions of Windows, it was operating in kernel space, basically. It wasn't just a user space, it was a part of the kernel. It was a part of the kernel actually executed. So you were directly giving commands to the kernel. So whenever you typed dir, I don't know, cp command, rm to remove, cp to copy, and so on, you were directly giving commands to the kernel. So if you gave a malformed command, if you gave something malicious, you could potentially crash the kernel. And it wasn't really that difficult. For example, there was this thing called a ping of death in the 90s. You were children back then. I don't know if you even were born back then. It was something very simple. It existed at the time of Windows 95, Windows 98, I think. The ping of death, you can check it online even now, was something very simple. Basically, a ping is just a command that you use in the networking environment in order to send a packet to another computer and to see if it responds. If it responds, well, basically that means that that machine is online, connected to the network and actually working. If it doesn't respond, that means there is a problem with the machine on the other end. So a ping is just a tool used in networking. The ping of death, on the other hand, was a means to attack Windows 95 systems. Because you see, there is a certain amount of data that you need to send with a ping package to the other side. If you send data more, if you send a longer amount of data than the data that is expected, the other side cannot interpret it. It has difficulties interpreting it and it crashes. Whereas normally it should be just checking whether it has received the right amount of data or not. And if it receives more than, let's say, 64 bytes, it should ignore the rest of it. But Windows was a really awful, sorry, but an awful operating system in the 90s. Nowadays, well, they have copied a lot of parts of the Linux system, so they are working a bit better. But in the 90s, it was an awful piece of software. So awful that if you send it more than 64 bytes, it would crash in a ping. And that's why it was called the ping of death. You could just ping a system and boom, it goes down. As simple as that. So very, very careful about how you manipulate commands and whether those commands are executed in the user space or kernel space and so on. In the Windows systems of the 90s, it was the Wild West, basically. The Wild West of operating systems. It was awful, really awful. I mean, the only reason why Windows got so popular is because basically the US government was supporting Bill Gates's Microsoft company at the time, because in terms of quality, their product was awful, just awful. Now here, of course, we have the standard directories under the root directory, bin for the binaries, boot for boot time data and code, etc for configuration files, home for the home folders, home directories of the users, and of course USR for the programs that have been installed to the system. Of course, there are many more. There are, for instance, there is, for instance, the proc, PRIC directory, which contains one directory for each process, and it contains all the status information, everything related to those processes. Now, there is a question, I believe. Yes, what's the question?
It was not a question, but I want to say that in Windows 10, if you try to access a global root, a file in a global root, the system crashes, gives a blue screen of death.
What do you mean? What do you mean the global root?
There's a path that when you try to access it, it throws an exception, but Windows is not catching that exception. The whole system crashes. It's a particular path.
Well, I'm not very surprised. I mean, this is only valid for the Unix and Linux system, this directory hierarchy. It is not valid for Windows. Now, we have not yet gotten to the part of differences between POSIX compliant and not POSIX compliant systems. Because Windows, all the flavors of Windows, from Windows 1 to 3 all the way to Windows 10, are not POSIX compliant. Windows, all the flavors of Windows are definitely not POSIX compliant. So the programs that you write on Unix and Linux systems, as you very well know already, are not portable to Windows systems, because Microsoft, ever since it has been established, has refused to be compliant with the POSIX standard, with the standard of portable operating systems. And that is why, for instance, one of the differences between POSIX compliant and non-compliant systems in the case of Windows is that it doesn't have a global root in the same sense that we have it in the case of Unix and Linux. Instead, we have the drives, as you very well know. We have the C drive, the D drive, E drive, and so on and so on. And each drive is its own root, if you will. That's an entirely different setup. Our course, this course, will be limited, only limited, with POSIX compliant systems. So systems that, not systems, but the standard itself. What is the standard telling us? What is the standard of portable operating systems? How do you code against the interface, the standard of portable operating systems? And that means the code that you execute, the code that you design, the programs that you implement will not be portable to the Windows systems, very probably. Mr. Kamil says, global root device kernel, if you type it on a browser, you get the blue screen of death. I'm sorry, turning it off. Now, we have a few minutes before we terminate. Now, of course, class, I mean, this is a part that you already know, so that's why I'm not saying that much on top of it. I mean, the root directory is, of course, the slash, and all of the files and folders underneath it are the children and descendants of this root directory. And of course, each file has a type, naturally. There are different types of files, the devices, the pipes, the sockets, directories, links, symbolic links. We will get to them. We will study each of these at a week, possibly the third week, that will be dedicated exactly to this topic on how the file system is organized. Ms. Pelin says, how does the operating system use PROC-ID maps for memory allocation? It doesn't use PROC-ID maps for memory allocation. This is basically just the, how should I put it, the registry, sicil kaydı, the registry of who is using what and what is the status of each process. Now, these numbers that you see in the proc directory, each correspond to a process, and these are the process IDs. For instance, let's go to, I don't know, let's pick a process. Let's go to number, I don't know, 10,644. Oh, sorry, we're already there. So 10,644. So this is the contents of the folder of 10,644. There are some things that are not accessible, of course, permission denied. And the rest of it we can see, for instance, in the mem right here, which normally contains memory-related information. And of course, we cannot access it right now. It is empty. Do not be fooled by the fact that the sizes of these files appear 0. They are not 0. They are not 0. They are not, in fact, actual files. The moment that you try to read them, they will be filled in. The moment that you try to read them. So, for instance, if I attempt to say cat mem, oh, where is it? Oh, yes. They belong to root right now, so I cannot really access anything. Let's go to 1064. Yes, if I type cat mem, permission denied, naturally. I cannot see what is going on in the memory details of this process since I am not a root user at the moment. So all of these files inside it, right here, each of them, they are a point of entry, if you will, to the statistics and the status information of this process. How much CPU it is using, which memory regions it has allocated, what are the signals that it is listening to, what files are open, everything. Everything is accessible through the proc folder. But it is a bit early right now to look into this folder since we haven't seen processes yet, so I'm not getting into too many details in order not to confuse you. So I believe that we're going to stop at this point for today. So we are at 10:24 at the moment. And together we will continue with the rest of it. So I will see you tomorrow at 8:30 in order to finish this overview. And yeah, and that's pretty much it.
Hello, Dr. Erhan. This is Habil.
Oh, merhaba Habil hocam. Yes, yes. Yes. Okay.
So,
yes, Habil hocam, please, you had an announcement. Please go ahead.
Okay, yeah. Thank you for accepting me for your course. It was nice. I have a chance to listen to your course. It was very nice. So I have an announcement for the students of this course. This semester I'm going to give the digital logic course, and also the laboratory is going to be handled by assistants. But the labs is going to be done in online version. So we are. I am here to ask for some tutor students. So I need 4 tutor students. And I am expecting to take these students from your course, because these guys in your course already took that course on the last semester. So I am asking for volunteers that who get a BB, minimum BB scores from the Digital Logic Lab. So those students who wants to be a tutor, please send me an email having your indicating your also course that you get from that course in the last semester. So what is going to be done in the laboratory, what we are expecting from these tutors. These students, we are going to have laboratory sessions for 6 sessions in 6 weeks in that semester. So those students are going to watch their the lab sessions online. It's going to take about 16 minutes. And then at the end of the lab sessions, we are going to have a kind of demo sessions that each student which has completed their task will make a demo to that tutors. Then these tutors are going to watch their demos for 6 minutes. And then later on, they will send these video recordings to the lab assistants. And then lab assistants are going to record their are going to score their marks. So the tutors are only expected to watch the sessions. It's going to take about, I think, 2 to 3 hours per session. So in semester, it's going to take about, let's say that 15 hours for a tutor. So, and also we are going to make, I think, a kind of, let's say that favor to that students. So if I think you will agree that one, if they get a minimum BB from your course, then they can get an extra a letter for their scores. That's it. Is there any students that wants to be a tutor? And any question for to being a tutor?
I'm sorry, only the students who get BB, at least BB, would get an extra letter note?
Yes.
All right,
So
thank you.
you have to take at least BB from system programming course to get an extra BB.
So if you get a BB from system programming and you have been a tutor, BB becomes a BA.
Yes.
And if you have BA, it becomes an AA.
Yes.
If you already have an AA, it doesn't do anything.
You cannot give it to your student, to your friend.
No. So you cannot exchange it for anything. Yeah.
Burada arkadaşlar şurada şunu da söylemekte fayda var. Dediğim gibi Logic'ten minimum BB almış olmanız gerekiyor geçen dönem.
Ha, yes. You also need a BB from the Logic. Yeah.
Evet.
Okay. Okay.
Bu arkadaşlar lütfen bana mail atın skorlarınızla beraber. Dediğim gibi sadece bir 15 saatlik bir vaktinizi almış olacağız dönem içerisinde. Sizin için de iyi bir deneyim olur diye düşünüyorum ben. Peki. Hocam çok teşekkür ederim.
Rica ederim hocam.
Dersiniz için de. Peki iyi günler arkadaşlar.
Sağ olun. İyi günler hocam. Okay, that's it class for today. It's 10:30, so unless something unexpected happens, I will see you tomorrow morning at 8:30 once again. These recordings, of course, will be available. The slides are online, and we will continue from where we left off. It was very nice hearing you again. Have a nice day, and see you tomorrow.
Have a nice day.
Thank you. You too.